given a matrix, we need to find LU decomposition of A. So we apply Gauss elimination process here. First, you do one thing, you identify what is the first non-zero element in the first row. So the first non-zero element is 3. So now I need to multiply the first row with 1 by 3. So when I do that, I'm going to get 1, negative 2, negative 1, whereas this is 2, 0, 6, negative 4, 7 and 4. And let me write L here. I am going to write L directly. Okay. So the first row we multiplied with 1 by 3. So here 3. 0, 0. Next. Anyway, this guy is also fixed. Why? Because we want a lower triangular matrix. Only thing you need to know these numbers. Okay. So the next time what shall we do? We need to make this one as 0 and as well as this one as 0. So to make them as 0, so I'll write R2 minus 2R1. So when you do minus 2R1 here, then here you should write plus 2. 2. The next thing, R3 minus, not minus, this is plus 4R1. So this is 3, 1. Now I added 4 here, then I have to subtract 4. So once if you do this, 1, negative 2, negative 1, 0, and this is 0 minus of this, which is 4, 6 plus 2, which is 8, and 0 minus 8 plus 7, minus 1, 4 plus 4 times of this, which gives me 0. Okay. So the next thing, we need to make it as an upper triangular matrix. To be upper triangular, this guy must be 0. So let's do that operation. So the next operation, oh wait. So we want the diagonal entries to be 1 here. So let me make this as 1. Okay, so to make it 1, so let me multiply with 1 by 4. So that is R2 multiply with 1 by 4. So when I do that, now let us multiply the second row with 1 by 4. So R2 with 1 by 4. So 1, negative 2, negative 1, 0, 1, 2. So now here I need to write 4. Why? Because here I multiplied with 1 by 4, then I have to write 4 here. So next, the third row, here we want 0 and in place of negative 1. So R3 plus R2. You need to see with the new row. Okay. So when you do that, this is 0 and 0, negative 1 plus 1, and 0 plus 2, this is going to be 2. And this will be minus 1. And what is the last element? So here I have 2, I want to make it as 1. So to make it as 1, you have to multiply with 1 by 2. So you'll get 2 here. So finally the matrix is this. R3 divided by 2, which is nothing but 1, negative 2, negative 1, 0, 1, 2, 0, 0, 1. So this is the upper triangular matrix U, and whereas this is the lower triangular matrix. And you can verify that when you take their product L times U, you'll exactly get A. L times U will be A. So here you see, is this the L we got? 3, 0, 0, 2, 4, 0, negative 4, negative 1, 2, and 1, 1, 1, minus 2, 2, okay, minus 1. So this is what A equal to L into U. I hope it is clear how to decompose a matrix into lower triangular times upper triangular matrix. Next, let us see how to solve a linear system with the help of LU decomposition. Now let's assume that you are given with a linear system, that is a into x equal to, let me take b here, let me take the linear system. So this is the linear system you are given with. Now they are asking us to solve it using LU decomposition. You know how to solve it directly, but we'd like to use LU decomposition and we'd like to solve it. And if you look at the matrix A is nothing but this, whatever we have taken earlier. Yeah, this is the matrix A, isn't it? The quotient matrix, if you observe that 3, -6, -3, 2, 0, 6 and -4, 7, 4, this. And LU decomposition of this is given here. So we are given with a linear system, that is AX equal to B, but we write it like this, LUX equal to B. So first we need to consider UX equal to Y as a new system. So first you have to take this, take UX equal to Y. And you solve for this guy, that is Ly equal to B. So let us solve for it. Ly equal to B, which is nothing but L, you know what is it? 3, 0, 0, 2, 4, 0, -4, -1 and 2. And this multiplied with -3, -22 and 3. Oh, sorry. This multiplied with y1, y2, y3. So y1, y2, y3, this is equal to -3, -22, 3. Yeah, from this you can easily solve what is y1. 3y1 equal to -3. So from this we got what is y1. y1 equal to -1. Next, from the second expression, 2y1 plus 4y2 is -22. You know what is y1, that is -1. So from this 4y2, which is nothing but -22, and this will be +2. So which will be -20. From this you can see what is y2. y2 is nothing but -5. So we got y1 and y2. Next I need to find what is y3. So that is 4 times of y1. y1 is -1 plus -1 time of y2, which is -5, plus 2 times of y3, which is nothing but 3. So 2y3, which is nothing but 3 minus 4 minus 5. So we obtain -6 from this. y3 equal to -3. So we got y1, y2, y3. Now using this y1, y2, y3, now we are going to solve this system. Ux equal to y. Now let me write Ux equal to y. So we know what is the upper triangular matrix here. 1, 1, 1, 0, 0, 0. I need to write these entries. -2, -1, 2. -2, -1, 2. This multiplied with x1, x2 and x3, which is equal to y. We know what is y, -1, -5 and -3. Am I correct? Yeah. So now from here you can see what is x3. x3 is nothing but -3. Next, from the second expression, x2 plus 2 times of x3. x3 is actually -3, which is equal to -5. So x2 is nothing but 1. Next I need to find what is x1. So x1 minus 2 times of, you know what is x2. x2 is 1 minus 1 time of we know what is x3, that is -3, which is nothing but -1. So now x1 equal to -1 plus 2 minus 3. So we get -2. Therefore x1 equal to negative 2. Therefore, solution of the linear system, that is x equal to this minus 2, 1 and minus 3. So this is how you can simply solve a linear system using LU decomposition. So if you are asked to solve it using LU decomposition, you need to decompose the matrix like L into U, then you need to solve it this way. Okay, so I hope you understand this. See, we should remember one thing in this process. We are not making row changes. We are not interchanging rows here. Okay. So if you like to get into a lower triangular form or an upper triangular form, if you are interchanging rows, it doesn't work here. I mean, for example, given a matrix A like this, 1, okay, let me write 0, 0, 1, 0, 1, 2, 1, 0, 1. Let's say you have this matrix. Now my question is it possible to make this as a lower upper triangular matrix without interchanging rows by using some row operations? The moment you are interchanging rows, then we say that it do not have LU decomposition. Okay, so now think about this problem. See here, you try to see one thing. Suppose if I write if I make row changes, let's say if I make the first row and third row interchanges, then it's not A, it's the new A, which is 1, 0, 1 and 0, 0, 1 and 0, 1, 2. And this is exactly in an upper triangular matrix, isn't it? R1, R1 minus R3 and R3, R3 plus R1. But in the Gauss-Jordan elimination process, is that the way we do the things? So when we apply row operations, first of all we identify the pivot elements, and we do row operations with the pivot row only. It means the row which contains pivot. And whatever we did here, like R1 minus R3, R3 plus R1, it looks like what is it? Interchanging rows itself. Okay, let me do one thing. Let me apply this row operations, whatever you suggested. So the suggested row operations are R1, you make it this way. What is it? R1 minus R3 and R3 R3 plus R1. Okay. So now let me write a matrix to update the elementary, to update these elementary operations. Okay, so it may not be lower triangular if you observe. Let me write it. So if I update it to R1 minus R3, so that is 0. Okay, wait. R1 minus R3. So negative 1 and 0, 0. Okay, so here also I have to do the same thing. Okay, let me write the elementary matrix, not to have confusion. So the elementary matrix, what you did here, R1 we replaced with R1 minus R3. So that is 1, 0, minus 1. See, now here itself it says whatever you are getting here, it is not a lower triangular matrix. Why? Because you are getting an element here. It means you are not getting a LU decomposition. The moment you make this operation, it means the lower triangularity is, failed. Anyway, here you'll end up with an upper triangular matrix, but If you look at the elementary operations, the elementary matrices, when you take their product, you do not get a lower triangular matrix. Okay, but if you follow the procedure, like you take the row which contains the pivot, and with respect to that, we are making row operations. Okay, so we are coming from the first row, next the second, next third, next fourth. Like we follow a sequence there in the elimination process. We don't do some random operations. Maybe to make our life easy, sometimes we may to solve a linear system. But when it comes to the process, we have an algorithm for that. Do we get UL? It's interesting. You're saying you will get UL. Okay, you try it and send me. So, but I can say one thing. For this matrix, we do not have LU decomposition. But if you facilitate that row interchange operation, then I can say that it has this decomposition LU times P, PLU decomposition, where P is the matrix which takes care of interchanging rows. Okay, this P is the matrix which takes care of interchanging. For example, if you ask me what is P in this case, just the first row to the first row to third row to first, right? So 0, 0, 1, 1, 0, 0, 0, 1, 0. This is what my P. Now A is equal to P times L times U. Where I wrote P, you may ask me what is L. L is nothing but the identity matrix. Why? Because directly we got an upper triangular matrix there. And where U is nothing but 1, 0, 1, 0, 1, 2, 0, 0, 1. That's it. Okay. So this matrix has PLU decomposition, not LU decomposition, where P is the matrix which takes care of interchanging of rows. Okay. Now from LU decomposition we can obtain one more decomposition. Yeah, before looking at it, let me ask this question. Is LU decomposition unique? Is LU decomposition unique? You not maybe, be certain. See, for example, to see whether this LU decomposition is unique or not, let me look at the previous case. Where is the decomposition? Here it is, right? So can I write this decomposition like this? Instead of having 3's here, I'd like to have 1 here. It's like 1, 0, 0 and 2, 1, 0, negative 4. I should be careful. I'll do one thing. Why to change all? It is enough to give different L and different U, right? So when you multiply this 3 times of the first 3 times of the first row, that's what I'm going to get it here. So but I want to have it 1. So when you have it 1, then multiply the first row with 3 here. So this is 3, negative 6 and negative 3. And the rest I'll write as it is. 2, 4, 0, negative 4, negative 1 and 2. This is 0, 1, 2, 0, 0, 1. Now you see, this is also gives you L into U. It is a lower triangular, that is an upper triangular. This L is different from the L what I wrote here, and U is different from this. Now you tell me, is LU decomposition unique? Yes. LU decomposition need not be unique. So answer to this question, no. It's not unique. You can always manipulate this way. I gave 1. Similarly here, if you want to make 1, yes, you can make 1. Accordingly, you can make change here.
సార్ ఇన్ ఎల్లో చేంజ్ చేయాలి సార్ 2/3 వేయాలి.
Which one? L
2/3 అండ్ -4
2/3.
పెన్తో రాసేస్తారు సార్.
This one.
సార్ అక్కడ ఎల్లో 2/3 -4/3 సార్ ఫస్ట్ కాలమ్.
Oh, this one you are saying 2/3. Ha, yeah, correct. Why? Because I removed 3 here. The first column 1 times of this. So 3 times of this. Yeah, correct. You're correct. 2/3 and 4/3. Why? Because 3 times of the first column will be the first column of A. Correct. Yeah. So now the next question. So okay, we answered this question. LU decomposition is not unique. Now we got LU decomposition of A. We wrote A is equal to L into U, and we know this is possible when no row change is needed in the Gauss elimination process. If there is no row change, then definitely we can say that LU decomposition exists, and we can write that decomposition. Now I want to express this LU decomposition into this form: L into a diagonal matrix into U. Is it possible? Maybe not same L and same U. New L, new lower triangular matrix, new upper triangular matrix. So this is my aim. I would like to convert a matrix A into a lower triangular, into diagonal, into an upper triangular matrix. Is it possible? Can easily answer this question. Why? Because the moment you have L into U, then you want to keep some diagonal matrix in the middle. So let me take the previous example. So what is the previous one? Yeah, here it is. So now I got A equal to L into U. So now I'd like to get the diagonal matrix as this. Whatever entries you have it here, that is 3, 4, 2, and the rest of them I'll keep it as zeros. Okay, now I need to write what is the new upper triangular matrix here and what is the new lower triangular matrix here. See, you do one thing. You don't do any changes for U. U, let us write it as it is. -1, -2, -1, and 0, 1, 2, and 0, 0, 1. Let us write it as it is. Now, let us try to express this L like this. L equal to L prime into D. This is how. So now when you multiply these two, I should get L. That's the aim. So here definitely you'll have 1, whereas here you'll have 2/3 and you'll have -4/3. So when you multiply, the first column will be 3 to -4. Next, the second column, this is 0 and it is going to be 1, and this is -1/4. So when you multiply with 4, you'll exactly get 0, 4, -1. Next, this is 0, 0, 1. That's it. So now we got an LDU decomposition. So this matrix A can be expressed as L times D times U. Okay, and similarly we have other decompositions. When you start with a symmetric matrix, when A transpose is same as A. So when you look at its LU decomposition or LDU decomposition, A can be expressed this way. You'll get it like L D L transpose, and it is possible to get it like U transpose D U. Okay, you do one thing, you start with a symmetric matrix. Start with a symmetric matrix and try to make it as, try to get LU decomposition. That is enough. You just get LU decomposition. What is the transpose of a lower triangular matrix? Is it an upper triangular matrix? For example, if I take lower triangular matrix, right? 1 2 3 0 1 5 0 0 6. So when you take its transpose, what is it you get? 1 2 3 0 1 5 0 0 6. So you get an upper triangular matrix. So what you're getting is LDU only. Since A is symmetric, so we should get this also symmetric. So definitely you're going to have LDU L transpose. Why? Because when you take its transpose, you'll get again LDU. LD L transpose. Okay, so these are the other decomposition, LD L transpose and U transpose DU for a symmetric matrix. This is for a symmetric matrix. Right? Yeah, and people do solve problems using LU decomposition, LDU decomposition, and similarly, PLD decomposition as well, PLU decomposition as well. Okay, so now we are left with, we are left with singular value decomposition. That is what we need to discuss. SVD, singular value decomposition. But I'd like to continue this in the next session. Okay, so I'll stop it here.